Hello everyone, welcome back to Physics-Based Animation. Now, in the last video, we learned all about cloth simulation, and we saw how we could leverage finite element methods to simulate thin sheets of cloth, like this. In this video, we leave deformable objects behind and take our first trepidatious steps into the wide world of rigid body simulation. Over the past few videos, we spent a lot of time building up a familiarity with all things wiggly, and the algorithms we can use to simulate them. Before we move on to simulating rigid objects, we must first answer an important question. What makes an object rigid? What is the essential property we must preserve in rigid body simulation? To answer that question, we are going to need some of the concepts we've already developed for the simulation of deformable objects. One of the key elements of both our volumetric and cloth finite element simulations was the deformation gradient. This 3x3 matrix F was instrumental in measuring the amount of local deformation that an object was undergoing. The role of the deformation gradient was to tell us how an arbitrary vector between 2 points in an object's reference space was transformed when the object was deformed into the world space. And we used this deformation gradient to come up with a formula that measured the difference in squared lengths between an undeformed vector and its deformed counterpart. Let's start by asking ourselves what we expect the strain to be for a rigid object. Well, intuitively, because the rigid object does not stretch or deform in any way, we assume that the strain, this difference in squared lengths, should be zero. And we can see from our strain measure that this implies that the deformation gradient transposed, multiplied by itself, should equal identity. This simple formula tells us that for an object to be rigid, F transpose must always be the inverse of F and vice versa. Matrices that have this special property are called orthogonal. In 3D, there are two main geometric transformations that yield orthogonal deformation gradients. The first is a rotation. This intuitively makes sense since we've all seen rigid bodies rotate in space. The second is a reflection. And the problem with reflection is that physically it corresponds to having the object pass through itself. And this is something we want to avoid. This constraint that rigid bodies rotate means that our deformation gradient F can't just be an orthogonal matrix. It must be a rotation. We can specify this by saying that F must belong to the special orthogonal group, which is the group of all orthogonal matrices with positive determinants. In other words, matrices that don't stretch or deform an object and also don't reflect it. And while we can do a lot with just rotations, it's pretty clear that in the general case, a rigid object can do more than just that. Rigid objects can move between points in space without rotating at all. And that's because rigid bodies also translate. So now that we've identified the allowed types of transformations for a rigid body, we can start building up a mathematical model for rigid body kinematics. And just like with the finite element simulations we've worked on in the past, this journey starts by establishing a mapping from the reference space of an object to its pose or configuration in the world space. So here we can see that we have a time-varying rigid body mapping that can map any point on our reference bunny to a point in the world space. Now, when we did this for finite element simulation, our mapping was extremely expressive, and we relied on additional potential energies to rein in deformation. In the rigid body case, we are instead going to ensure that this mapping only allows for rotation and translation of our object. We do this using the conveniently named rigid body mapping. This mapping takes a point in the reference space, rotates it around the origin, and then translates it into the world space. It should be pretty obvious from this equation that our object can only rotate and translate. Furthermore, if we compute the deformation gradient by taking the derivative with respect to capital X, we see that F would be just a rotation matrix, R. And this is exactly what we required to make the object rigid in the first place. So now that we have this mapping between spaces, we can start turning our variational mechanics crank, starting with identifying the generalized coordinates of a rigid body. Here's our rigid body mapping with rotation and translation clearly identified. In fact, the rotation R and the translation of the origin P are the only variables in this mapping, the only knobs that are available to change the world space configuration of our rigid object. And so we choose these to be our generalized coordinates. An important note is that unlike all the previous methods explored up to this point, our rotation and translation are different mathematical objects, a matrix and a vector. This means that there's no convenient stacked vector of generalized coordinates here. Instead, our generalized coordinates Q are a set composed of these two elements. This won't affect our derivations much, but it's good to be reminded that our approach is not limited to needing big vectors of generalized coordinates. Now that we have generalized coordinates, let's move on to working out the generalized velocities. In the previous videos on mass spring systems and finite element methods, it was always pretty obvious what the generalized velocities were. They were the time derivatives of nodal positions. While you have likely already guessed that the generalized velocities are related to the time derivatives of our rotation matrix and our translation, we have to do a bit of work to find their particular form. To start with, let's compute the velocity of a single point on our rigid object, which we do by taking the time derivative of our rigid body mapping. The result of this, unsurprisingly, is that the time derivatives of our generalized coordinates make an appearance. P dot is relatively intuitive. It's just the velocity at which the origin of our reference space is moving in the world space. Here we call it linear velocity to distinguish from the velocity of our rotation matrix. And this term will take a little work to unpack, because rotation matrices are special orthogonal matrices, which are going to need a special representation of the velocity to hold this whole thing together. What happened to r dot in this equation? Well, we used a special formula for the time derivative of the rotation matrix to express it in terms of another special three-dimensional vector, omega, and omega is called the angular velocity vector. Its magnitude, or length, encodes the speed at which the object is spinning, and its direction encodes the axis of rotation. The derivation is interesting enough to warrant its own video, so see the link in the video description below. Before we move on, I want to draw your attention to the square brackets enclosing capital X. These brackets indicate that you should use the vector capital X to build the so-called cross product matrix. This matrix gets its name because multiplying it with another vector will perform a cross product. With a little bit of rearranging, we can pull our angular and linear velocity out front, and we'll use these two terms as our generalized velocities, q dot. Here, because both terms are 3x1 vectors, we can indeed stack them up into a single 6 vector for convenience sake. And now, with generalized velocities in hand, we can continue down our familiar path and derive the kinetic energy of a rigid body. As has become commonplace, we start by expressing the kinetic energy of an infinitesimal volume, d omega, of our rigid body using the density rho and the squared magnitude of the instantaneous velocity at a point capital X. With the total kinetic energy given by integrating up these infinitesimal amounts of kinetic energy. And we have to integrate over the entire volume of our rigid body. And the greatest hits continue as we express the squared velocity magnitude as the velocity transpose itself. And this means we finally arrive at a rigid body specific step in our derivation. A quick reminder that we already have an equation for the velocity of a point in our rigid body. Now we just need to stuff it into our kinetic energy formula. After taking advantage of the fact that our leading rotation matrices cancel out due to orthogonality, we arrive at the following formula for kinetic energy, where this term, sandwiched between our q dot vectors, is the full mass matrix. We separate this mass matrix into time-varying matrices A, which take care of properly rotating our angular velocity vector, and a 6x6 constant matrix M sub 0, which requires integrating over the rigid body domain to compute. Before we dive in and start integrating, we can take some steps to make our lives a little bit easier, but to do this, we need to take a bit of a detour and learn about an important geometric property, the center of mass. The center of mass of an object is a point in three-dimensional space defined as the density-weighted integral of all points inside an object divided by the total mass of the object. We can use the center of mass to define a new reference space which has its origin at this point. And we do this by translating our original reference frame. We call this a center of mass coordinate system. Now, why would we do this? Well, to see the advantage, we have to go back and look at our integral. Here's our m sub 0 integral again. Kinetic energy is invariant to translation, so moving our rigid body in the reference space should not affect the value of this integral. This means that we are free to evaluate our integral in the center of mass coordinate system. Like all such integrals, we can approach this by integrating in a component-wise fashion. So let's start this process by looking at these off-diagonal terms. Let's dive right in and do this integral in the center of mass coordinate system. Step 1 is to substitute in our expression for capital X bar, which is just our original reference coordinate minus the center of mass point. Next, we split up our integral and notice that because the center of mass point is constant, our second integral is just integrating the density over the object, and that this is really just computing the total mass of the object, which leaves us with the following. Now recall that the center of mass C is just the density-weighted integral of capital X divided by the mass. This means that the two terms in this integral are equal, meaning that the answer is in fact 0. And this illustrates why the center of mass coordinate frame is so useful. It converts m sub 0 into a block diagonal matrix, and this leaves us with only two blocks left to integrate over the volume of the rigid body. When we did this for volumetric FEM, we split our object into tetrahedra and used these small elements to evaluate volumetric integrals. But this seems heavy-handed for a rigid body, and it introduces the additional complication of requiring a volumetric mesh. Ideally, we would do our volumetric integral using only the surface triangle mesh of our object. Taken at face value, this might feel like a little bit of dark magic, but we'll see that using a single powerful identity will enable this incredibly useful functionality. Okay, so we're back, and we're going to do this volume integral using only the surface triangles of our rigid body mesh. To see how this is possible, we will need to take another minor detour to talk about the divergence theorem. The divergence theorem says that the volume integral of the divergence of a vector-valued function is equivalent to the surface integral of that same function dotted with the outward-facing surface normal. Let's see how we can apply this to integrate up our rigid body mass matrix. And to get some insight into how this will work, we need to look at the terms in our matrix integrand. What we notice is that all the terms are sums of monomials, so constant values along with scalar components of capital X bar and various products. Because these functions are 1, not particularly complicated, and 2, defined over our whole rigid body, we will be able to apply the divergence theorem to transform our volume integral into a surface integral. Let's take a look at how we do this by examining one of the simplest terms in this matrix, the value 1. Here's our integral. We just want to integrate the density over the volume of our shape. Coincidentally, this computes the mass of our object, which we've seen is useful to compute the center of mass point. Now, in order to apply the divergence theorem, we need to express this integral in terms of a divergence over the reference space. For monomials, this just requires a bit of integrating, which yields the following. You can confirm these two equations are equivalent by computing the divergence itself. Now that we have a divergence operator, we can apply the divergence theorem. And this converts our volume integral to a surface integral. Here, capital N is the surface normal in the reference space, and gamma is the surface of our rigid body. Now we just need to evaluate this surface integral on our triangle mesh. And we can do this by splitting it into per triangle integrals and summing up all the results. Here, gamma sub j indicates the domain of the jth triangle, and capital N sub j is the surface normal of the jth triangle. The final question is, how do we integrate this function over a triangle? We can re-express the components of capital X bar using barycentric coordinates phi sub 0, phi sub 1, and phi sub 2. We learned how to compute the triangular barycentric coordinates in the previous video on cloth simulation. And now we can re-express our integrand as a function of these barycentric coordinates. That's going to look a bit like this. Finally, we can integrate this using the standard formula for barycentric integration. And because h is a polynomial function, this integral can be evaluated by hand or using symbolic math software. We can repeat this procedure for all the terms in M sub 0 to finalize the computation of the mass matrix. Once we are done, we end up with a block diagonal matrix where the upper left block is the rotational inertia matrix and the lower right block is the mass of the object times a 3x3 identity matrix. This gives us a nice concise form of our mass matrix. In fact, we can shorten this even more by folding our A matrices back into M sub 0, which leaves us with the final form of the rigid body kinetic energy. And now we can move on to the potential energy. So what is the potential energy of a rigid body? Well, in our previous attempts, the potential energy was used to introduce a notion of elasticity into our model. Here we have no elasticity as our object can never deform. This means that our potential energy is always 0. There's no elastic potential energy stored by a rigid body ever. Consider the simplicity of the potential energy term a small reward for all the work done in service of the kinetic energy, which is really where all the complications lie. Now that we have kinetic and potential energies, we can finally derive our equations of motion. So here's our rigid body Lagrangian, where all the action is happening in the kinetic energy term. One potential difficulty is that our rotations appear inside the rigid body mass matrix. That means that for the first time we have a kinetic energy that is a function of not just the generalized velocity, but the generalized coordinates as well. We can plug everything into our Euler-Lagrange equations, and of course we'll power through all these derivatives, but we have to take special care with the rotations. And if we do this just right, we arrive at a very famous pair of equations of motion known as the Newton-Euler Equations. Here, our first equation expresses the conservation of angular momentum in terms of the angular acceleration and applied external torques. But we also see the appearance of this mysterious term known as the quadratic velocity vector, which results from the mass matrix depending on the generalized coordinates. Our second equation expresses conservation of linear momentum in terms of center of mass acceleration and external forces. Let's talk about our external force and torque terms quickly. Previously, we thought of forces as single vector-valued quantities applied to a single point of a simulated object. For a rigid body, applying a force, say pulling on one part of the object, can induce both a translation and a rotation, and this occurs because this applied 3x1 force vector induces both a linear force on the center of mass and a torque, a rotating force, around the center of mass. We need a way to convert our force into these two components. To do this, we are going to need a very important matrix called the rigid body Jacobian, here denoted J. J is a 3x6 matrix, and it's the matrix that converts generalized velocities to a 3x1 pointwise velocity for some point capital X bar. Given a force applied to a point of our object in the world space, x, our first step is to compute capital X bar that maps to x, and we can do this by inverting the rigid body mapping. Once we compute capital X bar, we can compute the rigid body Jacobian at this point. Then, to convert the 3x1 force vector to a 6x1 stacked vector of torques and center of mass forces, we multiply the force vector by the Jacobian transpose. We can then substitute our values for the external force and external torque back into our equations of motion, and then integrate. And this leads us naturally to the final question, which is, how can we numerically integrate the Newton-Euler equations? Now, these equations are a pair of decoupled ordinary differential equations, so we can derive discrete update equations for each one independently. Let's do this starting with the conservation of linear momentum. You've probably already realized that we've seen this equation before. It's just the equation of motion for a single free-floating particle in space. Accordingly, we can discretize this using a simple forward-Euler time integration scheme. And here we can use forward-Euler time integration because there's no stiff term, no spring penalty, or elastic potential that can cause instability. With that done, we can move on to the conservation of angular momentum. Here's our conservation of angular momentum equation, and we can start by discretizing the angular acceleration using a first-order finite difference. Combining this with an explicit discretization of the forces and quadratic velocity vector, we arrive at a forward-Euler update for our angular velocity. Now that we can update our angular velocity, we need to figure out how to use angular velocity itself to update the rotation of the rigid body. And this is a little bit tricky. Up until this point, we've been discretizing accelerations and velocities using finite differences. Unfortunately, naively applying this approach to our rotation matrix update will lead to non-orthogonal updates, which violates our rigid body assumption. Let's see if we can come up with a slightly different way of doing this that will allow us to preserve the orthogonal characteristic of the rotation matrix. Typically, we derive update equations by discretizing time derivatives, and in this class we've been using first-order finite differences for this discretization. Our issue now is that it's not totally clear how to derive a finite difference update that respects the special orthogonality constraints of our rotation matrix. Fortunately, there's another perspective we can take when deriving these update rules, and that perspective is through the lens of ordinary differential equations. Specifically, we can view these update rules as coming from the solution to an initial value problem with appropriate initial conditions. Here, we are deriving an update rule for the velocity of a particle So we choose our initial conditions, the position of the particle at time t sub 0, to be the particle position at the beginning of the current time step. And as a brief reminder, we can solve these equations analytically. Here, because we are assuming velocity is constant across the time interval, we can simply rearrange and integrate both sides. And this will recover our update rule. We have a constant of integration c, and that constant of integration has the value x of t from the initial conditions. So this approach worked equivalently well as a tool for deriving our standard time discretization. Let's see if we can use it to derive an update rule for our rotation matrix. To start, we need to write an equation that describes the velocity of a point on our mesh as a function of our rotation matrix R. We can do this using the standard angular velocity equation, which describes the velocity of our point as a function of the angular velocity around the center of mass, p. Defining the new variable y, we arrive at the following differential equation, which we can clean up a bit more by introducing our cross product matrix. And finally, we need to add some initial conditions. Now we just need to solve this equation. What's nice about this ODE is that it is separable and therefore has a known solution. And that solution is given in terms of the matrix exponential. Substituting our definition of y back in gives us the final answer. And we can see that the new rotated position of our point around the center of mass is given by multiplying our current rotation matrix by a matrix exponential. And it's this multiplication that gives us our update rule. Which means we can finally finish off these update equations. The complete set of update equations for the conservation of angular momentum then looks like this, where here we can evaluate our matrix exponential using the very handy Rodriguez rotation formula, which I'll leave as an exercise for the viewer to look up on Wikipedia. Finally, let's put all our update equations together. Now these four equations describe the crucial steps involved in integrating the motion of a rigid body through time. Even though there's some extra complication in the rotational component, in the end we arrive at a fairly concise explicit integration scheme. Now to be clear, as with deformable simulations, there are many integration schemes for rigid bodies, including implicit schemes. However, explicit schemes are quite popular due to their ease of implementation and the fact that they are quite stable for objects that are rotating with a relatively small angular velocity. And this is the result. Once we've got this all coded up, we get a nice spinning rigid body that we can pull on and throw around this scene. Even in this simple case, you get quite enjoyable rotations and behavior, and so this is quite a lot of fun to play with. However, as much fun as it gets even more interesting when we bring more rigid bodies to the party. And that's exactly what we will do in the next video, wherein we will discuss how to simulate objects made of collections of rigid bodies connected by joints. Now this will open the door to simulating things like this robot, so if being on the forefront of the robot revolution sounds like a good time, remember to watch next time. As always, thanks for watching, and hopefully I'll see you again.